because eventually we want to be able to actually use it to prove interesting things, not just stupid things like the fact that 6 is easy. So see, we can prove kind of interesting math things. We can also, a cool thing we can do is we can write functional programs, but then like actually prove things about them, like prove that this program will always, do X, Y, Z, or will always have this correctness property. Like in the same language, we could write the code. And actually, this is what some people do. So one practical way that people use Agda, I mentioned that it has a backend that can like translate it to Haskell. But of course, when you translate it to Haskell, all the proof stuff kind of goes away because Haskell isn't able to do that. But you could write a program in Agda and prove things about it, prove that it is correct, whatever correct means in that case, right? And then just like automatically translate it to Haskell. So now you have Haskell code that you can run as part of your Haskell project, but you actually have a formally checked proof that it has whatever properties that you want, right? So that can be a powerful way. If there's like some critical piece that you're like, I really, really want to make sure that this thing, never has a bug. Right, so that's kind of where it is. So, picking up where we left off. So we had this data type even that represents proofs that a natural number is even. Okay, so the type actually includes a natural number, and basically we just designed it so that anything of type even n we're thinking of as a proof that n is even. We proved that 6 is even, we proved that 8 is even. So one thing I want to show you a couple things about this. So one thing. Let's prove that 6 is even again. So I'll call it 6 even prime. So we argued why, obviously we have to use ZE or SSE. We can't use ZE because that doesn't have the right type. That's even 0. So we have to use SSE. And then the question is like, what number should go here? Well, obviously, since this will give us even of successor of n, if we want even 6, then obviously n has to be 4, right? Like there's nothing else it could possibly be. And you don't even have to think hard about what evenness means. You just, even if you didn't know what this meant, you could just look at this definition and be like, well, if you want even 6, this is suck of n, so you better give 4 here if you want 6. So in fact, Agda can figure that out. Well, actually, we saw that Agda can figure out the entire thing, but if I put an SSE, right, so here, this is where we want the natural number, and I can put an underscore here. So underscore in Agda means something a little different than in Haskell. In Haskell, it means, I don't know what goes here yet, but at least you can tell me what type needs to go here, right? It's a hole. So in Agda, the way we make holes is with a question mark. But an underscore means you figure it out. Just figure out what has to go there and fill it in. If there's like a unique thing that goes there, then fill that in. And I don't care. So that's, right, we can put, of course we can put underscores on the left side of the equals, just like in Haskell, if you don't care about an input. But we can put an underscore on the right side of the equals also if Agda should be able to figure it out. And there's like, I don't actually care about writing this, it's boring. You figure out what has to go there. And of course the reason that's even possible is that you can have types like this that have, in this case, the type has a number in it, and it can figure out things about like what number this has to be based on looking at the types. Okay. So underscore means okay. So I could keep going. I could put an underscore here. So this works too. Right now I can reload it just to make sure. So it's happy to just figure out, I can figure out what things must go there, so I'll just kind of fill it in the background. So the other thing we can do then is we can say, well, why do we even have to put the number? Right? Why do we have to give it a number as an argument at all? We have to because otherwise like n wouldn't be defined. We have to say what n is. here's a way to say, yeah, I know there has to be an n, but I don't want to actually have to give it as an argument. You just figure it out all the time. And it doesn't matter so much for this example, but we're going to use it a lot for other things, so I'm going to show you. So I'm going to make, I'm going to copy paste this and make, I'm going to call it EvenI, or even I for implicit. And you see how we had this argument n here. Instead of in parentheses, I'm going to put it in curly braces. The curly braces mean it is an implicit argument, meaning we don't actually have to, like when we use that, when we use SSE, it really does take n as an argument and then even IN as an argument, but we don't actually have to write the first argument. Agda will just fill it in. Curly braces. Implicit argument that we don't have to write. Agda should just fill it in all the time. So if I can now prove 6 even, I'll say even I6. Okay, so now, of course I still have to use, I need to, actually, you know what? Yeah. So here's another fun thing. Notice that I forgot to change the name of these constructors, ZE and SSE, because we're already using those for, even, and I'm using them for EvenI. Actually, Agda's okay with this. Basically, it can tell them apart by the types. It's like, this thing, you're trying to make something of type EvenI, so clearly you must mean this SSE and not the other one, because this is the one that makes sense. Haskell's not willing to do this, right? Haskell will yell at you that it doesn't know, like you have multiple things defined. Now, this might be confusing, so maybe you don't want to do this, but it would be a choice about whether it's readable to humans, not whether Agda cares. So, but notice it only made one a hole there, and if I ask about it, so Control C, Control comma will show you like what the okay. It tells me your goal is create even I4, and I have to create even I2. So there really are still those numbers being filled in there, but they're just kind of being filled in automatically. We don't have to write them. That's nice. Now, one other place that we see implicit arguments show up a lot, which is actually this was already happening in Haskell. We didn't think about it this way. If I make let's say the identity function, right? In Haskell we would write something like this: a arrow a, right? And the little a means it can be any type. And I think we mentioned that really in Haskell that actually means this, right? And it's kind of like first you get to pass it an argument, which is what type it should be, and then you pass it something of that type. So in Agda, in Haskell, in Agda, the way we write this is like this. It literally, that type, A, literally is an argument to the function. So I can say, usually we use a capital A in Agda, I don't know why. No, I don't have to, I'll use lowercase a. So A is some type, which we write set in Agda. And then we're going to take something of type A and return something of type A. But I put this in curly braces because the point is, just like in Haskell, just based on what we use it on, if we use it on a natural number, it's like, you must want the type to be natural numbers. So I'll just fill in that for you. Right? I could actually, here, let's just do it. I say like ID of, I don't care what the type is, X equals X. So with the type as an explicit argument. if I say, you know, ID, oh, right? This way, I have to, when I call ID, I actually have to tell it what type I want to use. So, for example, I could say ID natural numbers, and now I have to give it a natural number, 3. Right? And it's just going to return 3. But I can also make an implicit version that says, no, I don't want to have to actually tell it the type explicitly. I just wanted to figure out the type based on what I... So now if I say ID prime of 3, it's like, oh, 3 is a natural number, so that A must be natural number, so I'll fill it in. Haskell is doing this too. It's just that, like, in Haskell, there's like one specific instance where it will fill in arguments for you, which is basically when you kind of pass a type as an argument. It's just like a special built-in thing in Haskell. But in Agda, it's not really a special built-in thing. It's just like we can say whatever arguments we want. They could be types, they could be values. We can mix them up, and then we could say whether we want them to be filled in automatically or not. And of course, if it can't figure out what it is, then it's going to yell at you, right? But if it can figure it out, then it. Questions so far? Garrett?
Is that somewhat similar to when Haskell does the equals arrow and gives the type of, like say order or something, and then it'll give the...
Yeah. It is. So Haskell, that's another place where Haskell kind of implicitly fills in arguments for you when you have like a type class. Okay. So if you have a function that's like, you know, ord A, double arrow, A arrow something, right? It's both implicitly filling in like what A is. It's also implicitly filling in like information about how ord works for that thing, right? So it's really like at runtime it's passing around a little record of functions. It's like, okay, you need to do the ord stuff, you know, here's something. And yeah, it fills in that stuff implicitly. There is a way to do type classes in Agda. I don't remember how it works. But it definitely uses this kind of mechanism for doing implicit stuff. Okay. Any other questions? All right. The next thing I'm going to do to introduce a few more things is let's prove that 5 is not even. So first, let's see what would happen if we tried to prove that 5 is even. Okay. So if we try to prove that 5 is even, even 5. Okay, so we can make a hole, and it's like, yeah, you're trying to prove that 5 is even. So if I like hit Control C, Control R to refine the hole, right? It looks and says, well, we can't use ZE because it's not 0, but we can use SSE because it's 2 more than something else. So it's like, yeah, sure. All right, let's use the EvenI. We don't have to write those extra arguments. So it's like, yeah, that's fine. We can use SSE, but then what you're left with is you have to prove that 3 is even. That makes sense, right? If 3 was even, then 5 would be even, according to our rules. So I can try refining this again. It says, yeah, now you have to prove that 1 is even. So what's going to happen now if I try to refine it again? Because if we look back at, here, let's come back right. I want to pull up our definition of right? What constructor could we possibly use here to make a proof that 1 is even? So ZE doesn't work, because that's a proof that 0 is even, not a proof that 1 is even. SSE won't work either, because that makes a proof that successor of something is even, and 1 is not successor of something. It's just successor of 0, right? So actually neither of those match. And so we should see some kind of error if we try to refine it. It says no introduction introduction forms basically means constructors, right? So it's like, yeah, there's no constructors that could possibly fit here. And try as I might, there's nothing that I'm going to be able to fill in the hole here that will make it accept this, right? But that's not a proof that it's not. That's just, all that shows is that maybe I'm not clever enough to come up with the right way to prove it, right? I mean, okay, yes, in this case, we can look at it, we can be like, yeah, obviously you can't, but just the fact that I can't make one, maybe it's just I'm not smart enough. Okay, so can we actually use Agda to prove that it is not? And we can. So this doesn't work, but how to prove it's not possible. So for that, we're going to have to introduce not. And here's how we define not. So first, remember how we had, when we talked about propositional logic, we had this thing bottom that looked like an upside down T, and it kind of corresponded to false, right? But there was no way, there was no introduction form for it. There's no way to prove it. So the way we write that in Agda, let's say theta backslash odd, which is a set where, so this is, well, that's it. I don't want any constructors for it, right? It should not be possible to prove this. So there's no constructors. And Agda is perfectly fine with this. It's like, sure, fine. State type, yep, but there's no constructors. Okay. And then we're going to define not. This is like backslash neg. So I put the underscore, right, which means like you apply not, it's a prefix thing you're applying to a thing. So this is going to have type. And this is where things get a little mind-bending, right? Because we can just declare functions that work on types or on values or right, mix them up. So not. So you could think about the version of not that like takes a boolean and gives a boolean. That's not what I'm writing down here. Right? I'm taking the one that basically takes a type and turns it into a different type. So, you know, if you have a type that represents proofs of something, then not of that will represent proofs of not that. So it's actually going to be a function that takes a type and returns a different type. And the way it's defined is not P. We can just define it as P implies bottom. Hopefully this kind of makes sense intuitively, right? One way to think about something being false is that if you assume that, then like you get a contradiction or you get false, right? And we'll see that this actually is it's a great way to define not. Like it all works out nicely. So this, I mean, like, because it shouldn't be possible to ever get something of this type, right? If it were actually possible to get something of type P, then we could use that to create something of type bottom, but we can't. So this is a different way to say, yeah, you can't get something of type P, you can't prove it, because if you could, then you could prove this impossible. Right, and this is why I don't think we've talked about this like in detail. It was maybe like a level 2 problem on a problem set or something. But like, this is why not wasn't built into the version of propositional logic that we wrote down. Right? We didn't define not anywhere. It's because you can just define it in terms of implies and bottom. And this is great. So let's now see if we can prove. So I want to say 5 is odd. I want to say it's not true that EvenI odd. Okay. So how are we going to prove this? So remember, right, we just defined not as implication, right? E implies bottom. So actually, if I kind of expand this out, and the way you can do that is I think you do this word, no. Maybe we can't do it in this. Does it say up above? Maybe not. Okay. We'll just have to do it in our heads. So, I mean, this is the trade-off with having this version of Agda in a web browser. In some ways, it's super nice, and you don't have to deal with getting Agda installed on your computer, which can be annoying. But there's some things that you get when you do have it installed on your computer that this just doesn't. This supports like a subset of stuff. So there's a way to say, yeah, show me the goal, but try to expand all the definitions as much as you can to show me what it really means. It doesn't look like there's a way we can get that here, but anyway, we can kind of do it in our head in this case, right? Even I5, not even I5, really means even I5 implies bottom. Okay, so it's really a function, right? We're actually supposed to define a function that takes a proof that 5 is even, and then uses that to return a bottom somehow, right? So I can actually fill in an argument here, and this argument would be a proof that 5 is even. So I'll just call it even 5. Okay. So, and if I look at my goal now, this is, yeah, okay, now your goal is to prove bottom, and what you have is even 5 is a proof that even I5, that 5 is even. I guess this is a little, it's like upside down maybe, the way we're used to seeing rules. But it's always going to list the goal, but I guess, it's not really a rule. It's just lists the goal at the top, and then under it, it lists all the things that you have, all the variables that you have. So this can be useful. They're okay, where am I now? Let me look at this whole, hit Control-C, Control, comma, which I'm pretty sure is one of the things that it mentions up there. Yeah, Control-C, Control, comma says display the goal in context. Right, so it's here's what you're trying to prove right now, or here's what needs to go in this hole, and here's all the things that you have that you could potentially use. Any ideas how maybe I can proceed? I don't have too much to go on, right? But I do have this even 5 thing. Maybe is there anything I can do with that? Anything I can do with that? What do I do every time I have some input? Pattern match on it, right? That's always the answer. The answer is always pattern match. Not always, but a lot of the time. I mean, it's well, what else can I do? I have this input. Has this data type. Maybe I can pattern match on it and see what it looks like. I mean, I kind of already know what it looks like. It's going to have to look like SSE something, I guess. Can't be ZE. I mean, we also know that this shouldn't be possible, so we'll see what happens. So if I say pattern match, so I type in the name and hit Control-C, Control-C, case split, and it says, yeah, there's only one possibility. It has to be an SSE, and actually now the name is not a good name anymore, right? Because I think if we look at the goal, we'll see that actually this thing we have now is a proof that 3 is even, right? I can change the name. Well, I guess I can pattern match on that, right? It says, yeah, well, the only thing that could possibly be is an SSE. Okay, and let's call it presumably, supposedly, I have this argument of type EvenI1. But we kind of already had seen that this doesn't look like this would be possible, right? This can't be ZE, that doesn't have the right type. It can't be SSE either, because that wouldn't have the right type. That would be successor of successor. So what's going to happen if we pattern match in this? And actually, this will work. Because I'm not trying to make one. I'm saying, yeah, what if you have one? Then what? And if I try to pattern match on it, Agda is going to realize, wait, that's not possible. Like, there is no possible constructor this could be. Therefore, you don't actually have to handle this case. Because it's impossible, right? If I'm defining a function, and, if some input is, like, impossible, then I don't have to define what I should do when I get that input, because it's not possible to get it. Okay? So when I pattern match, something magical happens. It puts some empty parentheses there, which means this can't possibly happen. And then I don't have to fill in a definition, because it's not possible. So this is kind of just saying, like, yeah, you can define this function. It's kind of like the empty function that doesn't have any inputs and doesn't give any outputs, because the input is not possible. You can't possibly get something of that type, I think. So the parentheses is the absurd pattern, i.e. something that can't possibly happen. In that case, you won't have to define an output. Okay? Cool. And yeah, I mean, Agda could have, if I just did Control-C, Control-A, Agda could have filled in that whole proof for us like that. But we'll see cases later where I can't fill in the entire thing. Cool. Any questions so far? Obviously, you all know you can't answer questions. Yeah, Silas.
So it's the parentheses because there's no way to represent one.
Yeah, well, the thing that would go here would have to be something of type EvenI1. And it can look at the different possible constructors for EvenI and be like, this one doesn't work, this one doesn't work. None of these constructors could possibly give me something of that type, so it just fills in the parentheses and says, it's not possible. Can't happen. And it has to like go in a few steps, right? Because just looking at EvenI5, you can't tell at that point that it's not possible. You're like, yeah, it could be SSE. That looks possible. Then I would need something like EvenI3. So it has to like go a few steps before it's like, okay, wait, no, it's actually not possible. But yeah, it could fill in. I think, pretty sure if we just say, well, I don't know if it could. Could it fill in a proof? Try this. If I say Control-C, Control-A. It actually couldn't figure it out. It says no solution found. So maybe, yeah, it's still like, I guess it's not willing to pattern match automatically. So we kind of have to do that. Like force it to be like, oh, let's try pattern matching on this input. And then see what happens. But notice, like, all I had to do actually, all I really had to do is say, okay, pattern match on E. And then I said, all right, pattern match on E again. Pattern match on E again. Like, I didn't really have to type any of that. I just, like, told it to keep pattern matching on E and it filled it in. So. Cool. What was the next thing I wanted to do? We proved that 5 is not even. Oh, I know what I was doing next. So, as a way to introduce some more stuff. So we have this data type that we think represents evenness. Now, but in general, if you're defining some data type of proofs, right, you're saying, like, here's some property that I have in mind, and I'm going to write down a data type that represents that property. Like, Agda doesn't know what you intend, right? As long as it's a valid data type, it's like, sure. So, you could, like, make a mistake in how you encode that, like if we had accidentally put in, like, for example, what if we left out one of these sucks by accident? Right? Like this now, like you can make one of these for any number now, because It's just like, well, if 0 is even, then 1 is even, and 2 is even, and 3. So it's something, but it doesn't represent evenness anymore. So, you know, there's various ways that you can try to convince yourself that it's doing the right thing. So one thing we can do, that I would like to do, is I think did we write down, oh, we didn't actually. Well, we can do this. Let's make a function that takes a natural number and returns true or false. That says whether it's even. And then let's actually prove that those correspond. That like, if that function is going to return true, then that means we can make a proof that the number is even, and vice versa. Like if there's a proof, then the function is going to return true. So, we're going to make an even function. And this is going to actually be a function that just takes a natural number and returns a boolean. So, good old-fashioned, like, we're going to test whether numbers even or not. So how should I do this? Well, let's pattern match on n, of course. So is 0 even? Yes, 0 is even, right? Do you have a capital T? Yes. What should I put here? The successor of n even? I mean, it might, well, it could be, right? I don't know. So what should I put?
This few cases.
So you want to do more, like pattern match and some more? There's a few different ways you can do it, actually. Let's do, so actually, I think it's going to be the easiest if we do it like this. Let's pattern match on n one more time. And we'll say, all right, so now I have this case. Successor of 0, that's 1. So that's not even. So this should be false. And in this case, I say, well, if it's successor of something, I just want to check if that n is even. Right, so is even. Does that make sense? So then I want to prove, so how can I prove that is even and even I are about the same thing? Right, I really want, I want to prove something like, you know, is even n, something like, for all n, is even n is true, you know, if and only if even I n. So like if I can prove that n is even using this even I thing, then the function should return true, and vice versa. Right? So we have most of the ingredients we need to write this down in Agda, except the equals part. Because for all n, well, this is actually interesting. Let's think about this for a second. How would we write down like a for all in Agda? So a for all is really just a special kind of function. It really says, look, if you give me any n, then I can give you a proof of this thing about n. That's really a function. It says you input an n and I'll output a proof. So actually, like for all doesn't correspond to anything special in Agda. It's just we can just write down a function that takes n as input and then outputs a proof value. The if and only if, I mean, we could define that. We could also just write it as like this implies that and the other one implies this. But we need the equals. So the table to talk about equality. So we can just equality, you know, equals is not built into Agda. We just define it, and this is a little mind bending. And I don't expect you to understand exactly how the definition, like all the pieces of how the definition works, but I think we can understand like how to use it and kind of what it means. Okay. So I'm going to define. This is a standard name for it. It's like the triple equals thing. So you write it with basically, we're saying, we're defining what it means for two things to be equal. It's polymorphic, so it can work for any type A. And it's going to take, again, don't worry about like why there's like, why is this thing on the left of the column on the right, but basically it's taking two A's. Like there's one here, and there's one over here. It's taking two A's as arguments, and then it returns a set that is like, we're defining some type of proposition, right, or some type of, like, what does it mean to have a proof that two things are equal? So, there's only one way to prove that two things are equal, which is if they're literally the same thing, then they're equal. And this doesn't seem like this should be enough, but it turns out it is. So REFL stands for reflexivity. REFL says, okay, so you can basically read this as the only way to prove that two things are equal is if they literally look like the same thing. They're equal. Or the only way to directly construct a proof they're equal is they literally look like the same thing. But we'll see that we can actually we can build up these proofs in other ways where they don't literally look the same, but we can still prove that things are equal. So just as practice, so this encodes the property of reflexivity, right? But equality has a few other properties that we usually like it to have, like transitivity, like if A equals B and B equals C, then we want A to equal C. Right? And we can actually write that down. It says, okay, for any type A, and if I have, call it X, Y, and Z, type A. And incidentally, right, if you have multiple things with the same type, you can just like smush them all together like this. I could also write X colon A, arrow, Y colon A, arrow, Z colon A, but I can just put them all together. Then, right, this is really like saying for all X, Y, Z. Because if you give me three things, X, Y, and Z, then I will output a proof that, well, also if X equals Y, and if Y equals Z, then we will output a proof that X equals Z. Right, so we can say, okay, for any set A, for any values X, Y, and Z of that type A, if you give me a proof that X equals Y and a proof that Y equals Z, then X equals Z. Okay, let's see how we prove this. So I can say and actually, you know what? I'm going to make these implicit also, because once we have these things, it can obviously see what X and Y and Z are supposed to be just by looking at the types of these things. Here's another fun thing about Agda is that names, like in Haskell and probably most other languages you know, there's like very specific characters that are allowed to be part of names. Like it's like, letters, numbers, but numbers can't come first, underscores, that's it. Maybe a prime, like in Haskell. Agda's like, you can have whatever the heck characters you want in names. The trade-off is that you always have to put spaces around everything. So you can't, like, if you want X plus Y, like in Java or something, you can put X plus Y with no spaces. And it's like, well, that's not a valid name, so it must be X plus Y. But in Agda, X plus Y would be a valid name. So if you want to do plus, you have to actually put spaces in these things. That's the trick. So this is like, what is this thing? This thing is this argument is a proof that X equals Y. So I'm going to give it the name X equals Y, which just helps me remember like what the heck that thing is. So Y equals Z. All right. So somehow I'm given this proof that X equals Y. I'm given this proof that Y equals Z. I need to prove that X equals Z. What should I do first? What do you think? What's always the answer? Pattern match, right? Because, well, like, what are these things? These things are proofs of equality, and right up here we see that there's only one possible way to construct something of that type. So if I pattern match on it, maybe that'll do something. So I'm going to pattern match on X equals Y, and something funny is going to happen. So let's, actually wait, before I do that, Yeah, so actually, let's look at this first, right? So it's showing us, here's all the stuff you have, right? You're trying to show x equals z. You've got this thing, y equals z, you've got x equals y. There's also all these things. Notice it says not in scope, because those are implicit arguments, so like we can't actually talk about them. But it's just like, yeah, that's, you know, you have these things, they're kind of there, but you can't talk about them. If we wanted to, there's a way we could, but we don't need to. So I'm going to pattern match on x equals y. So okay, it said, all right, yep, it's REFL. But here's the funny thing. REFL only works if the two things were literally the same. And so by doing this, like this was a proof that x equals y, but since this is REFL, I guess x and y must actually be the same. So we actually learned, by pattern matching, we learned, or Agda learned, oh, x and y actually are the same thing. So if we look again at the goal, it says our goal is still to prove x equals z, but something funny happened here. You see what happened here? So you have this thing y equals z, but notice the type that it says it has now. It says it has type x equals z. That's because it figured out, by doing this, that x and y are the same. So it just like substituted x for y here. So x and y everywhere, like, and also like, there's no y here anymore, because y and x are actually the same. Well, now what should I do? I mean, now we're done, because look, we're trying to prove x equals z. Look, I have something that says x equals z. So I can just put that as the output. That works. Or, if I wanted to, I could also pattern match on y equals z. And it's like, that shows me that y and z are also the same. And so now I just prove that x equals x. Because now it's like, yeah, x, y, and z are all the same thing, so now I can just say REFL if I want. So it definitely, even to me, after I know about this, it still feels a little magical. It's like we didn't really do anything, but basically there's enough stuff kind of built into Agda that it knows about what does it mean for things to be the same or be different. Not really be different, I guess be the same. We're kind of building on that and then writing down some properties of equality. So we can also prove it's symmetric, but I'm not going to bother. So let's at least write it down. So for example, we could say maybe we'll just stop. There's nothing really to do in like 2 minutes. So. Okay, but next time, now that we have equality, right? Well, actually, we can like write this down and prove